In the past 12 months alone, astronomers have confirmed the existence of more than 300 new worlds orbiting distant stars. Places that, until recently, didn't exist in human knowledge at all. These are not theoretical predictions or mathematical possibilities. They're confirmed planets with measured sizes and orbital periods. Worlds that have joined the ever-growing catalogue of places beyond our solar system. The pace of discovery has reached a level that would have seemed miraculous just a generation ago, when finding a single planet around another star was cause for global celebration. You're listening to The Drowsy Astronaut, where tonight we explore the newest additions to humanity's map of the cosmos. Some of the most fascinating worlds discovered in 2024 and 2025. This is a 2-hour journey that unfolds slowly, without any rush, meant to help you drift through the cosmos after a long, stressful day. Wherever you are as these words reach you, and whatever time it happens to be, I'm glad you've chosen to spend a little of your evening learning about places that were unknown until recently. If you'd like to share where you're listening from, the comments are always open. And if this kind of calm exploration helps you unwind, a like or subscribe helps this channel continue. The discoveries we'll explore tonight will still exist tomorrow, unchanged by whether you remember every detail or simply absorb the sense of a universe that keeps revealing new wonders. Whenever you're ready, let us begin. Among the most striking recent discoveries is a world that should not exist according to models developed just a decade ago. A planet roughly the size of Neptune, but with a density suggesting it is almost entirely made of iron. The planet orbits its star so closely that its year lasts only a few hours, and its surface temperature likely exceeds 2,000 degrees Celsius. Yet despite these extreme conditions, the planet has persisted for billions of years, stable in an orbit that brings it closer to its star than Mercury approaches our Sun. The discovery challenged assumptions about how dense planets form and survive. This iron world is not alone in defying expectations. Another recent find orbits backward, compared to its star's rotation, spinning in the opposite direction from every other planet in its system, as if it remembers a violent past that flung it into its current strange configuration. Such retrograde orbits suggest histories of gravitational chaos, close encounters with other planets that redirected trajectories in ways our orderly solar system never experienced. A third peculiar discovery from this period involves a planet that appears to be losing its atmosphere in real time, streaming gas into space as its star's radiation strips away the outer layers. Observations caught this evaporation in progress, measuring the escaping material and estimating how long the planet has left before its atmosphere is entirely gone. The world is dying slowly, transforming from a gaseous sub-Neptune into whatever rocky core might lie beneath. We are witnessing planetary evolution happening on human timescales. The telescopes responsible for these discoveries work continuously, gathering data whether humans are watching or not, accumulating the observations that eventually reveal new worlds. TESS, the Transiting Exoplanet Survey satellite, continues its systematic survey of the sky, now well into its extended mission and still finding planets around stars both near and far. The James Webb Space Telescope adds depth to breadth, characterizing atmospheres of planets that TESS and earlier missions discovered but could not study in detail. Ground-based spectrographs measure the wobbles that planets induce in their host stars, providing masses that complement the sizes measured from transits. The collaboration between these instruments multiplies what any single facility could achieve, creating a network of observational capability that spans the electromagnetic spectrum and reaches across the globe and into space. A planet candidate identified by TESS might be confirmed by a ground-based radial velocity measurement, then characterized atmospherically by Webb, with each step adding layers of understanding that transform a data point into a known world. The process takes months or years, but it proceeds steadily, adding planets to the catalogue at a pace that would have overwhelmed astronomers of previous generations. The catalogue itself has grown to include more than 5,700 confirmed exoplanets as of early 2025, with thousands of additional candidates awaiting the follow-up observations needed for confirmation. Each confirmed planet represents not just a discovery, but a sustained effort of observation, analysis, and verification that ensures the detection is genuine, rather than an artifact of noise or instrumental effects. The standards are high because the stakes are high, because claiming to have found a new world carries weight that demands certainty. Some of the newest discoveries orbit stars so close to our solar system that their host suns are visible to the naked eye on clear nights. Points of light that ancient observers knew and named, without any suspicion that planets might accompany them. One recent find orbits a star in the constellation Eridanus, only about 30 light-years from Earth, close enough that future telescopes might directly image the planet, rather than merely inferring its existence from indirect effect. The proximity makes such worlds particularly valuable, accessible to observations that more distant planets cannot support. Another nearby discovery came from a star that had been monitored for years without revealing any planets, until improved analysis techniques applied to archival data extracted a signal that earlier methods had missed. The planet had been hiding in plain sight, its presence recorded in data collected long before anyone recognized what the data contained. Such rediscoveries from existing archives demonstrate that the catalogue of known planets includes only those we have learned to see, not all those that observations have already captured. The red dwarf stars that dominate the stellar population have proven particularly rich in recent discoveries. Their small sizes and low luminosities making planetary transits easier to detect and habitable zones accessible to current instruments. Planets around red dwarfs orbit closer to their stars than Earth orbits the Sun. That the reduced stellar output means these close orbits can still receive appropriate amounts of energy for liquid water. Many of the newest potentially habitable worlds circle these small, cool stars that will shine steadily for trillions of years. The variety of newly discovered worlds spans nearly every category that exoplanet science has defined, from hot Jupiters scorching in the radiation of their nearby stars to cool super-Earths in the outer reaches of their planetary systems. Some discoveries fill gaps in the known population, occupying regions of size and temperature space that have been strangely empty. Others add to already populous categories, confirming that the patterns observed earlier reflect genuine cosmic preferences rather than observational biases. The radius gap, a curious shortage of planets between about 1.5 and 2 Earth radii, has received particular attention as new discoveries either confirm its existence or reveal exceptions that help explain its origin. Planets in this size range are rare, perhaps because atmospheric loss transforms larger sub-Neptunes into smaller rocky cores, while leaving planets outside this range relatively untouched. Recent discoveries of planets within the gap provide crucial data for testing theories about this peculiar feature of the planetary population. The period ratio between planets in multi-planet systems has also attracted scrutiny, as many systems show planets in or near orbital resonances where their periods form simple ratios like 2:1 or 3:2. New multi-planet discoveries either add to the resonant population or demonstrate that resonance is not universal, that some systems escaped the gravitational locks that others settled into. Each new system with measured periods contributes to understanding how planets migrate and interact during the chaotic early phases of system formation. The human stories behind these discoveries involve teams of researchers working across continents and time zones, analyzing data, writing code, checking each other's work, and eventually publishing results that add to the permanent scientific record. Graduate students complete dissertations based on planet discoveries that began as unexplained signals in datasets, transforming careers as they transform knowledge. Senior scientists who have spent decades refining techniques see those techniques applied to data of unprecedented quality, revealing worlds that earlier instruments could never have found. The announcements of new planet discoveries come through multiple channels, from peer-reviewed journal articles to NASA press releases to social media posts by excited researchers who cannot wait for formal publication. The community learns of significant finds almost in real time, with preprint servers hosting papers weeks or months before they appear in journals. This rapid dissemination means that the newest discoveries become known quickly, integrating into the collective understanding before the traditional publication process completes. The public follows major discoveries with interest that varies with the perceived significance of each finding. Potentially habitable worlds generate headlines that reach general news outlets, while technical discoveries of equal scientific importance pass unremarked except by specialists. The gap between public attention and scientific importance is sometimes wide, with genuinely revolutionary findings overlooked, while more photogenic discoveries attract cameras. The researchers themselves learn to navigate this landscape, communicating their work to different audiences with different interests. The months of 2024 brought discoveries that will influence exoplanet science for years to come, establishing priorities for future observations and challenging models that had seemed adequate before the new data arrived. Some findings confirmed expectations so precisely that they bolstered confidence in the underlying theories. Others raised questions that remain unanswered, puzzles that future research will address using instruments and techniques not yet available. The transition to 2025 continued this pattern of confirmation and surprise, with early months adding planets that both filled expected niches and defied existing categories. The stream of discovery shows no sign of slowing, as the instruments that find planets continue operating and the archive of data continues growing. What seems current tonight will seem historical within a year, superseded by still newer discoveries that push the frontier further outward. The catalogue of known worlds expands continuously, a library of places that exists in databases and scientific papers, and the minds of researchers who study them. But each one is real, a place that orbits a sun, a world that has existed for billions of years and will continue existing long after human attention turns elsewhere. Among the hundreds of planets discovered in the past year, a handful captured attention beyond the scientific community, generating news coverage and public discussion that brought exoplanet science briefly into the spotlight. These headline-making discoveries share characteristics that appeal to human curiosity: potential habitability, extreme strangeness, proximity to Earth, or properties that break previous records. The first discovery to generate major attention in 2024 involved a planet orbiting in the habitable zone of a nearby Sun-like star, a combination of properties that suggests conditions potentially suitable for life as we understand it. The planet is slightly larger than Earth, receiving stellar energy comparable to what our world receives from the Sun, and orbits a star similar enough to our own that imagining conditions there feels less like speculation and more like extrapolation. Headlines described it as a potential Earth twin, though researchers were careful to note how much remains unknown about the world's actual conditions. The caution is warranted because a planet in the habitable zone of a Sun-like star is not necessarily habitable in the sense that matters for life. The planet might lack an atmosphere entirely or possess an atmosphere so thick that surface temperatures are crushing. It might be covered in global oceans with no dry land, or be a bone-dry desert world where water never accumulated. The habitable zone describes where liquid water could exist in principle, not where it actually does exist. The headline-making discovery opened possibilities without confirming them. Follow-up observations of this particular planet are already underway, with astronomers using multiple instruments to learn more about its properties and potential conditions. Radial velocity measurements are refining the planet's mass, which, combined with its size, will reveal whether it is rocky like Earth or gaseous like a small Neptune. Atmospheric observations may eventually be possible, though the planet's size and its star's brightness make this challenging with current technology. The world that captured headlines will take years to characterize fully. A second headline-generating discovery involved a planet in a completely different category. A massive world orbiting so close to its star that its atmosphere likely contains vaporized rock, raining from incandescent clouds. This hellish environment captured public imagination precisely because it was so alien, so different from anything in our experience that it seemed almost fantastical. The planet glows with its own heat, hot enough that it emits visible light rather than just reflecting starlight. Observations revealed iron and other metals in gaseous form in its atmosphere. This scorching giant represents the extreme end of planetary environments, conditions so far beyond our experience that understanding them requires extending physics into unfamiliar territory. The atmospheric chemistry involves reactions that never occur naturally on Earth, with materials we consider solids floating as vapors and condensing into clouds, unlike any that form in our sky. The planet has become a laboratory for studying matter under conditions that no terrestrial experiment can reproduce. Scientists find it fascinating precisely because it is so extreme. A third major headline came from a discovery that broke a record. The planet with the shortest orbital period ever confirmed, racing around its star in less than 4 hours. This world completes a full year, while humans barely finish a morning meeting, its surface perpetually facing a star that dominates half its sky. The planet is so close to its host star that tidal forces have likely stretched it into a slightly elongated shape, and material may be streaming from its surface toward the star it orbits. The record-breaking nature of the discovery gave it news value beyond its scientific importance. Records in science are made to be broken, and the shortest period planet will likely lose its title to some future discovery that pushes the limit even further. But each record setter demonstrates what is possible, showing that planets can exist in configurations that might seem implausible before they are actually found. The universe proves consistently more creative than our imaginations, producing worlds in places where theory suggested nothing could survive. The discovery of planets around binary star systems generated another round of headlines during this period, with circumbinary worlds that orbit 2 stars instead of 1. These Tatooine-like planets, named for the fictional world in Star Wars where 2 suns set over the desert horizon, demonstrate that planet formation can succeed even in the gravitationally complex environment of stellar pairs. The newest circumbinary discoveries include a world potentially in the habitable zone, where 2 suns might warm oceans rather than 1. The visual appeal of 2 suns rising and setting drives public interest in circumbinary planets, beyond their scientific significance, which is considerable. Formation models must explain how planets coalesce in disks disturbed by 2 gravitational centers rather than 1, how they achieve stable orbits despite the complex gravitational environment, and why they end up at particular distances from their stellar pairs. Each new circumbinary discovery adds data that tests and refines these models. Atmospheric discoveries also generated headlines during this period, particularly when the James Webb Space Telescope detected molecules in exoplanet atmospheres that had never been found before beyond our solar system. The detection of sulfur dioxide in one planet's atmosphere, produced by photochemical reactions in its upper layers, demonstrated that Webb could identify not just the presence of molecules, but the chemical processes occurring in alien skies. Headlines translated this technical achievement into stories about alien weather and exotic atmospheres. The continuing investigation of K2-18b generated perhaps the most discussion of any exoplanet study during this period, as additional Webb observations refined understanding of its atmospheric composition and the tantalizing hints of possible biosignatures. The initial detection of dimethyl sulfide, a molecule produced primarily by life on Earth, remained controversial, with some analyses supporting the detection and others questioning it. The scientific debate played out in journals and at conferences, while headlines oscillated between optimism about possible life and caution about overinterpretation. This single planet has become a focal point for discussions about how biosignature claims should be evaluated, what evidence would be sufficient to claim detection of life, and how the scientific community should communicate uncertain results to a public eager for definitive answers. K2-18b will likely remain in the news for years, as additional observations either strengthen or weaken the case for biological activity. The world has become a test case for astrobiology. The planets that made headlines in 24 and early 25 represent different aspects of what captures human attention. Hope for habitable worlds, wonder at extreme environments, fascination with record-breaking properties, and the perennial question of whether life exists beyond Earth. Each headline serves as a gateway through which some members of the public encounter exoplanet science, potentially inspiring deeper interest. The famous planets introduce a field that contains thousands of less famous, but equally real worlds. The relationship between newsworthiness and scientific importance is complex, with some discoveries gaining attention out of proportion to their contribution to knowledge, while others of greater significance pass largely unnoticed. A planet that advances theoretical understanding without possessing headline-friendly characteristics may influence the field more than a famous discovery that confirms what was already suspected. The researchers themselves recognize this tension, valuing rigorous science while appreciating that public attention brings resources and support. Media coverage of planetary discoveries has become more sophisticated over the years, with science journalists learning to distinguish genuine breakthroughs from incremental advances and to communicate uncertainty honestly rather than overstating conclusions. The best coverage explains not just what was discovered, but why it matters, placing new findings in context that helps readers understand their significance. This educational function of science journalism serves the public good. The discoveries that will make headlines in the coming year cannot be predicted with certainty, but patterns suggest what might capture attention. More potentially habitable worlds will likely be announced, especially as Webb characterizes additional targets and TESS identifies more candidates around nearby stars. Record-breaking planets in various categories will emerge as surveys push sensitivity limits, and the ongoing search for biosignatures will continue, generating discussion whether or not definitive detections are claimed. The James Webb Space Telescope continued transforming our understanding of exoplanet atmospheres throughout 2024 and into 2025, applying its unprecedented infrared sensitivity to worlds discovered by earlier missions that could not characterize them in detail. Each Webb observation adds layers of information to planets previously known only as sizes and orbital periods, transforming abstract data points into worlds with measured temperatures, identified molecules, and atmospheric structures. The technique that enables these discoveries, called transit spectroscopy, exploits the moments when planets pass in front of their stars and a tiny fraction of starlight filters through the planetary atmosphere before reaching Webb's instruments. Different molecules absorb light at characteristic wavelengths, leaving fingerprints in the spectrum that reveal what gases surround the distant world. The signal is extremely small, typically less than 1 part in 10,000, but Webb's sensitivity allows detection of features that previous telescopes could not see. During this period, Webb detected CO2 in the atmospheres of several additional planets, confirming that this molecule is common among the sub-Neptune and gas giant planets accessible to current observations. Carbon dioxide had been detected on fewer than a dozen exoplanets before Webb launched, and the number has now grown substantially. The molecule's presence indicates atmospheric chemistry that might, under the right conditions, cycle carbon between surface and sky, as it does on Earth and Venus. Each detection adds to understanding of how carbon behaves on worlds vastly different from our own. Water vapor detections have also accumulated, with Webb confirming the presence of water in the atmospheres of hot Jupiters and sub-Neptunes at various distances from their stars. Water is the molecule most associated with life as we know it, and demonstrating its presence on exoplanets reinforces that the building blocks of habitability exist throughout the galaxy. The abundance of water varies among the observed planets, providing data that informs models of atmospheric formation and evolution. Methane proved more elusive than some predictions suggested, with several planets expected to show methane instead, revealing atmospheres dominated by other molecules. This absence of expected methane in some atmospheres indicates that chemical processes destroy the molecule faster than anticipated, perhaps through reactions driven by stellar radiation. The non-detections are as informative as detections, ruling out scenarios that models had considered plausible and pointing toward atmospheric chemistry more complex than simple equilibrium calculations. The hot Jupiter WSP-39b received extensive Webb observation during this period, becoming one of the most thoroughly characterized exoplanets known. Multiple instruments aboard Webb examined its atmosphere, detecting water, carbon dioxide, carbon monoxide, sulfur dioxide, and sodium in a comprehensive chemical inventory. The sulfur dioxide detection was particularly significant, as this molecule forms through photochemical reactions in the upper atmosphere, demonstrating that Webb can trace not just composition, but chemical processes occurring on distant worlds. 39b revealed how heat distributes across the planet, from the scorching day side that faces the star to the somewhat cooler night side that faces away. The temperature difference provides information about atmospheric circulation, the winds that transport heat around the planet. Models of atmospheric dynamics can be tested against these measurements, refining understanding of how exotic atmospheres behave under conditions that no laboratory can reproduce.
The observations of WASP
39b represent what thorough atmospheric characterization can achieve with current technology, a benchmark against which other studies can be compared. Not every planet can be studied in such detail, as host star brightness and planetary size affect what signals can be extracted. But the WASP 39b observations demonstrate the ultimate potential, the depth of understanding that patient observation with Webb's instruments can provide. The TRAPPIST-1 system continued receiving Webb attention during this period, with observations aimed at determining which of its 7 Earth-sized planets possess atmospheres and what those atmospheres might contain. Early results for the innermost planets suggested little or no substantial atmosphere, consistent with models predicting that the small, close-orbiting worlds would have their atmospheres stripped by their star's radiation. These null results, while disappointing for habitability hopes, provide important constraints on atmospheric survival around red dwarf stars. The outer TRAPPIST-1 planets, including those in the habitable zone, remain under investigation, their atmospheric properties not yet firmly established. Longer observation times and additional transits will be needed to detect or rule out atmospheres on these smaller, cooler worlds. The search continues, with each observation adding to the accumulated signal that might eventually reveal what surrounds these potentially habitable planets. Patience is required, as the signals are near the limits of what Webb can detect. The K2-18b observations that generated so much discussion involved tentative detection of dimethyl sulfide, alongside more confident detections of methane and carbon dioxide. The significance of dimethyl sulfide lies in its biological production on Earth, where marine organisms are essentially the only natural source. If confirmed on K2-18b, the molecule would require explanation, possibly through biological processes, though non-biological alternatives have not been ruled out. The scientific community has responded to the K2-18b findings with appropriate caution, recognizing that extraordinary claims require extraordinary evidence. Additional Webb observations have been conducted, with analysis ongoing to determine whether the dimethyl sulfide signal persists and whether its abundance is consistent with biological or abiotic sources. The planet has become a test case for biosignature detection, with methodological discussions about how to evaluate such claims becoming as important as the specific findings themselves. The atmospheric diversity revealed by Webb observations during this period defies simple categorization, with each planet presenting its own particular combination of molecules and conditions. Hot Jupiters differ from each other in ways that early models did not predict, with some atmospheres containing molecules that others lack, despite similar temperatures and sizes. Sub-Neptunes show even greater variety, their smaller sizes allowing wider ranges of composition and evolutionary history. This diversity is scientifically valuable because it provides multiple data points for testing theories rather than the single examples our solar system offers. Understanding why one hot Jupiter has certain molecules while another lacks them requires models that can predict atmospheric evolution across a range of conditions. Each new Webb observation either confirms these models or challenges them to improve. The coming years will bring additional Webb observations of exoplanet atmospheres, steadily expanding the sample of characterized worlds and deepening understanding of those already studied. Targets include more potentially habitable planets, more planets around nearby stars, and more representatives of categories currently poorly characterized. The queue of approved observations extends years into the future, with each program designed to address specific questions about atmospheric composition and structure. The transformation in understanding enabled by Webb represents a fundamental advance in exoplanet science, moving the field from knowing that planets exist to understanding what they are like. The telescopes that found planets through transits and wobbles revealed sizes and orbits, but left atmospheres mysterious. Webb fills this gap, revealing molecular compositions that transform abstract detections into worlds with measurable properties. The shift from discovery to characterization marks a new phase in how we know the cosmos. The patient accumulation of atmospheric data continues while you listen to these words. With Webb orbiting the Sun 1.5 million kilometers from Earth, its instruments cold and sensitive, gathering light that will be analyzed for months and years to come. The telescope works continuously, adding observations to an archive that will remain scientifically valuable for decades. The newest discoveries are being made right now. The Transiting Exoplanet Survey satellite has now operated for more than 6 years, far exceeding its original 2-year primary mission, and continuing to discover planets at a steady pace that shows no sign of slowing. The spacecraft orbits Earth in an unusual configuration that takes it as far out as the Moon's distance, allowing continuous observation of large sky areas while maintaining regular data downloads. The extended mission has already lasted longer than the primary mission that launched it. TESS was designed to find planets around bright, nearby stars, complementing the Kepler mission's survey of fainter, more distant targets. This emphasis on proximity means that TESS discoveries can be characterized in detail with follow-up observations, their host stars bright enough to support radial velocity measurements and atmospheric spectroscopy. The thousands of planets TESS has found or will find represent a population that can be studied comprehensively rather than merely detected. During 2024 and into 2025, TESS continued adding to its catalogue of confirmed and candidate planets, with announcement of new worlds arriving regularly through NASA press releases and scientific publications. The mission's fourth extended mission has refined observing strategies to maximize sensitivity to smaller planets in longer period orbits. The worlds that approach Earth-like conditions, but that produce smaller, harder to detect signals. The data processing pipeline that converts raw TESS observations into planet candidates has improved over the mission lifetime, with better algorithms extracting fainter signals from the brightness measurements. Planets that would have been missed by early versions of the analysis software are now being found in reprocessed data, demonstrating that the archive contains more worlds than initial analyses revealed. Each reprocessing pass through the data yields additional candidates. The candidate list maintained by the TESS team includes thousands of potential planets that await confirmation through ground-based follow-up observations or additional TESS data. Confirmation requires demonstrating that the brightness dips attributed to transiting planets are not caused by other phenomena like eclipsing binary stars or instrumental artifacts. The process is time-consuming but essential, as the catalogue's value depends on its reliability. Specific TESS discoveries from this period include planets around some of the nearest stars to our solar system, worlds close enough that future missions might characterize them in unprecedented detail. One such discovery orbits a red dwarf star only about 20 light-years away, receiving enough energy from its star to potentially maintain liquid water if atmospheric conditions permit. The proximity makes this planet particularly valuable for follow-up observations. Another notable TESS discovery involved a multi-planet system where the gravitational interactions between planets cause measurable variations in transit timing, allowing mass determinations without requiring radial velocity observations. Such systems provide complete planetary characterizations from TESS data alone, revealing sizes, masses, and densities that indicate whether the worlds are rocky, gaseous, or something in between. The transit timing technique works best for compact systems where planets pass close enough to affect each other significantly. Young planetary systems have been a particular focus of extended TESS observations, as these recently formed systems offer windows into planetary evolution that mature systems cannot provide. Planets around young stars are still cooling from their formation heat, their atmospheres potentially still changing as they settle into long-term stable states. TESS has observed numerous young stellar associations, finding planets that will help connect formation theories to mature system observations. The collaboration between TESS and ground-based observatories has matured over the mission lifetime, with established pipelines for alerting follow-up teams to interesting candidates and coordinating observations across facilities worldwide. A test candidate identified 1 week might have radial velocity confirmation within months, accelerating the pace at which candidates become confirmed planets. This coordination multiplies the scientific return from both space and ground investments. The overlap between TESS observations and other missions creates additional scientific opportunities, as planets observed by TESS can often be characterized by Webb or other facilities designed for atmospheric studies. The TESS-Webb pipeline has become particularly productive, with TESS identifying promising targets that Webb then characterizes atmospherically. This assembly line approach to planetary discovery and characterization maximizes the return from both major NASA investments. The observing strategy of TESS has evolved through its extended missions, with the spacecraft returning to previously observed sectors to accumulate additional data that reveals planets with longer orbital periods. During the primary mission, each sector was observed for about 27 days, sufficient to detect planets with periods up to about 2 weeks. The extended missions have observed some sectors multiple times, building baselines that can detect planets with periods of months or even longer. The statistics of TESS discoveries continue evolving as the catalogue grows, providing increasingly precise estimates of how common various types of planets are around different types of stars. The mission has confirmed that small planets are abundant around small stars, that multi-planet systems are common, and that the properties of planetary populations vary with stellar characteristics in ways that formation theories must explain. Each new discovery refines these statistical portraits. The sensitivity of TESS to different planet types depends on both planetary properties and stellar characteristics, with larger planets around smaller, quieter stars producing the most easily detected signals. The mission has found numerous hot Jupiters, whose large sizes and short periods make them obvious, but has also detected many smaller worlds whose signals required careful analysis to extract from noise. The balance between discovery efficiency and scientific priority guides target selection. The extended mission operations require ongoing funding decisions that evaluate TESS's continuing productivity against other potential uses of NASA resources. So far, the mission has consistently demonstrated value exceeding its cost, justifying continued operations. The spacecraft's health remains good, its instruments functioning within specifications, and no technical limitation currently threatens continued operations. TESS may continue discovering planets for years to come. The archive of TESS data continues growing with each sector observed, a resource that will remain valuable for decades as analysis techniques improve and researchers return to search for signals that earlier methods missed. Planets discovered in 2030 or 2040 may already exist in data collected during 2024, waiting for the improved algorithms that will eventually reveal them. The archive is an investment in future discovery. The graduate students and postdoctoral researchers who work with TESS data are learning skills that will transfer to future missions, building expertise that will serve the field for decades. The training function of mission operations complements the direct scientific return, creating human capital that multiplies the impact of NASA's investment. Each career shaped by TESS experience becomes part of the mission's legacy. The contribution of citizen scientists to TESS planet discovery has continued during this period. with volunteers examining light curves through the Planet Hunters test program and identifying candidates that automated algorithms missed. Several confirmed planets have citizen scientist discoveries in their pedigrees, demonstrating that careful human examination adds value even when sophisticated software handles initial screening. The public participation expands both the workforce and the engagement. The search for potentially habitable worlds gained new candidates during 2024 and early 2025, with discoveries of planets orbiting at distances from their stars where conditions might permit liquid water on their surfaces. These habitable zone planets represent the most sought-after category of discovery, the worlds most likely to capture public attention and scientific resources for follow-up observation. Each new addition to this exclusive list renews hope that somewhere among the stars, conditions suitable for life might exist. The habitable zone concept is simple in principle. The range of distances from a star where a planet receives enough energy to warm its surface above freezing, but not so much that water would boil away. The boundaries depend on stellar brightness, with dimmer stars having closer habitable zones and brighter stars having more distant ones. A planet in Earth's position would freeze around a dim red dwarf, but roast around a brilliant blue giant. The concept provides a first filter for identifying potentially habitable worlds. The reality of habitability is far more complex than the simple zone concept suggests. Depending on atmospheric composition, planetary mass, magnetic field strength, and numerous other factors that determine whether a planet in the right location actually maintains conditions suitable for life. A world without atmosphere in the habitable zone would have temperatures varying wildly between day and night, while one with a thick atmosphere might trap so much heat that its surface pressure becomes crushing. The zone is necessary, but not sufficient for habitability. Recent discoveries have added several planets to the list of potentially habitable worlds, each one requiring careful evaluation of what is actually known versus what is merely hoped. One particularly interesting addition orbits a K-type star, somewhat cooler and smaller than the Sun, at a distance that would provide comfortable temperatures if the planet possesses an appropriate atmosphere. The planet is roughly 1.5 times Earth's diameter, placing it in the size range where rocky composition is plausible, though not certain. Another habitable zone discovery from this period orbits a red dwarf star in a configuration that might provide stable conditions despite the challenges these small stars present. Red dwarfs are prone to flares that could sterilize planetary surfaces, and their habitable zones are so close that tidal locking likely forces planets to keep one face perpetually toward the star. Yet the sheer abundance of red dwarfs means that, even if only a small fraction host habitable worlds, the total number could be enormous. The James Webb Space Telescope has begun atmospheric observations of some habitable zone planets, searching for the molecular signatures that might indicate conditions favorable to life. These observations push Webb's capabilities to their limits, as the signals from small rocky planets in moderate temperature environments are far fainter than those from hot Jupiters that have been the easiest atmospheric targets. Early results have been inconclusive for some targets, with more observation time needed to detect or rule out atmospheres. The TRAPPIST-1 system continues receiving attention for its 3 habitable zone planets, worlds that might possess the temperatures and liquid water required for life as we understand it. Webb observations have not yet confirmed atmospheres on these specific planets, though the search continues. The concentration of 3 potentially habitable worlds around a single nearby star makes TRAPPIST-1 a uniquely valuable target, regardless of what future observations reveal. The concept of habitable zones around binary stars adds another dimension to the search, as planets orbiting 2 stars might experience conditions quite different from those around single suns. Circumbinary habitable zones are wider than single star zones because the combined energy from both stars contributes to planetary warming. Recent discoveries of circumbinary planets have included at least one that might fall within this expanded habitable region. The search for habitable zone planets has prompted development of metrics beyond the simple zone concept, attempting to quantify habitability in more nuanced ways. The Earth Similarity Index rates planets on how closely their properties match Earth's, while other metrics emphasize different factors thought important for life. None of these measures can actually confirm habitability, but they help prioritize targets for limited follow-up resources. Planets in the habitable zones of sun-like stars remain the most desired targets, as these systems most closely resemble our own and might host life most similar to what we know. The challenge is that sun-like stars are relatively bright, making the contrast between star and planet severe, and their habitable zones are far enough out that orbital periods are long and transits are rare. Finding Earth-like planets around Sun-like stars remains difficult with current technology. The Plato mission, scheduled for launch in 2060, will specifically target this challenging population, searching for transiting planets in year-long orbits around Sun-like stars. The mission is designed to detect Earth-sized planets, receiving Earth-like amounts of energy from stars similar to our Sun, the category of planet that most closely resembles our own world. Plato's discoveries will become priority targets for atmospheric characterization in the 2030s. The false positive rate for habitable zone planet claims warrants consideration, as the desire to find such worlds can lead to premature announcements that later require retraction or revision. Some planets announced as habitable zone discoveries have subsequently been shown to orbit outside the zone, or to have sizes inconsistent with habitability, or to have host star properties different from initial estimates. The scientific community has learned to view claims cautiously until multiple lines of evidence converge. The public appetite for habitable zone discoveries creates pressure that researchers must navigate carefully, communicating genuine findings while avoiding overstatement that could damage credibility. The most responsible announcements emphasize what is known, acknowledge what remains uncertain, and avoid language suggesting that habitability has been confirmed when only location within a zone has been established. The distinction between potentially habitable and actually habitable is crucial. The catalogue of habitable zone planets now numbers in the dozens, depending on exactly how zone boundaries are defined and which planetary properties are considered disqualifying. These worlds span a range of sizes, stellar types, and system architectures, demonstrating that planets in habitable zones exist throughout the galaxy. Whether any of them actually harbor life remains unknown, a question that may take decades or centuries to answer conclusively. The coming years will add more planets to the habitable zone catalogue. As TESS continues observing, ground-based surveys extend their sensitivity, and new missions come online. Each addition provides another target for atmospheric characterization, another data point for understanding planetary habitability, another chance that somewhere among the growing list, conditions suitable for life might actually exist. The search continues with patient accumulation of candidates and careful evaluation of each one's potential. The emotional investment in habitable zone discoveries is understandable, as these planets represent the possibility that we are not alone in the universe, that life might have emerged elsewhere in conditions different yet comparable to our own. This hope has motivated the search for exoplanets from its beginning and continues driving resources toward the goal of finding and characterizing Earth-like worlds. The newest discoveries carry this hope forward. The night sky that stretches above you now, wherever you happen to be, contains numerous stars with known habitable zone planets. Worlds where temperatures might permit, liquid water, and life might conceivably exist. These planets are invisible without powerful telescopes, but they are real, orbiting suns that shine among the stars you can see. The catalogue grows with each passing year, each new discovery adding to the map of potentially habitable real estate in our cosmic neighborhood. Not all recent discoveries fit neatly into expected categories, and some of the most scientifically valuable finds from 2024 and 2025 are planets that surprised researchers by defying predictions based on existing models. These strange worlds challenge understanding and drive theoretical advances as scientists work to explain properties that seem impossible according to current knowledge. The discovery of a planet with density exceeding that of pure iron presented one such puzzle, as formation models struggled to explain how such a massive core could form without accumulating significant amounts of lighter materials. The planet is roughly Earth-sized, but weighs more than 6 Earths, implying a composition dominated by iron, with little rock and essentially no water or atmosphere. Theories propose that the planet lost lighter outer layers to stellar radiation, or that it formed in an unusual environment depleted of lighter elements, but neither explanation is entirely satisfying. Another strange discovery involved a planet orbiting backward compared to its star's rotation, one of the most extreme retrograde orbits ever observed. Most planets orbit in the same direction their stars rotate, reflecting the common origin of star and planets from a single spinning disk of material. A retrograde orbit suggests violent history, perhaps a close encounter with another planet that reversed the orbital direction, or formation in a way that violated usual patterns. The planet carries scars of its past in its motion through space. Planets in extremely eccentric orbits, swinging from close approaches to their stars out to distant cold reaches and back again, challenge understanding of orbital stability and planetary climate. One recently discovered example varies its distance from its star by a factor of 10 during each orbit, experiencing temperature swings that would alternately roast and freeze any atmosphere. How such orbits form and persist for billions of years remains incompletely understood. The size distribution of newly discovered planets continues revealing the radius gap, a shortage of planets between about 1.5 and 2 Earth radii that divides smaller rocky worlds from larger gaseous ones. Planets discovered within this gap are particularly valuable because they provide clues about what physical process creates the division. Atmospheric loss driven by stellar radiation likely transforms some planets from above the gap to below it, stripping their gaseous envelopes to reveal rocky cores. Planets in very short period orbits, completing years in hours rather than days, push understanding of tidal interactions and orbital evolution. One recent discovery orbits its star in just over 4 hours, the shortest period yet confirmed, racing around a path that brings it closer to its star than any planet should survive. The extreme proximity generates tidal forces that may be gradually destabilizing the orbit, potentially sending the planet spiraling into its star over millions of years. We may be observing a planet in its final evolutionary stage. Young planets, still contracting from their formation heat, present another category of strange world, their properties differing systematically from mature planets of similar size and composition. Several recent discoveries around young stars have radii larger than expected for their masses, consistent with theoretical predictions that planets shrink over hundreds of millions of years as they cool and contract. These young worlds provide snapshots of planetary evolution that mature systems cannot offer. The atmospheric properties of some recently characterized planets have proven stranger than expected, with molecules detected in unexpected abundances or absent when models predicted they should be present. One hot Jupiter showed essentially no water vapor despite temperatures and compositions that should have produced abundant water, suggesting atmospheric processes that segregate the molecule vertically or chemically transform it faster than expected. Explaining these anomalies requires refined understanding of atmospheric chemistry under extreme conditions. Multi-planet systems with unusual architectures have been discovered during this period. Configurations where planets orbit too close together for comfort, or in arrangements that seem gravitationally precarious. One system contains 3 planets, locked in a precise orbital resonance, where their periods form simple ratios, a configuration that should be rare, yet keeps appearing in the data. Understanding why resonance systems are so common requires modeling the migration processes that can lock planets into these special relationships. Planets around binary stars present their own brand of strangeness, orbiting gravitational environments more complex than our single-star solar system. Circumbinary planets must navigate the varying gravitational pull of 2 stars that orbit each other, while the planet orbits both, a setup that creates zones of stability and instability, quite different from single-star systems. Recent discoveries have probed these zones, finding planets in configurations that test the limits of where stable orbits can exist. The inflated radii of some hot Jupiters remain unexplained despite decades of study, with these planets significantly larger than thermal models predict they should be. Something deposits extra energy in their interiors, puffing them up beyond expected sizes. But what delivers this energy remains debated. Recent observations have constrained possible explanations, without definitively identifying the mechanism. The puzzle persists. Planets orbiting pulsars, the rapidly spinning remnants of massive stars that exploded as supernovae, represent perhaps the strangest class of known worlds. The intense radiation environment around pulsars seems incompatible with planetary survival. Yet planets have been detected around several of these exotic objects. Recent observations have refined understanding of these systems, though how planets form or survive in such environments remains mysterious. The strangeness of newly discovered planets serves a scientific purpose beyond mere curiosity, as each anomalous world provides data that tests and extends theoretical understanding. Models that successfully predict typical planets gain credibility, while models that fail on strange cases must be revised or replaced. The outliers drive progress as much as the ordinary cases, highlighting gaps in understanding that need filling. The universe's creativity exceeds human imagination, a lesson reinforced by each discovery that surprises the researchers who made it. Planets exist in configurations that were not predicted, with properties that were not anticipated, in environments that seemed hostile to planetary formation or survival. The catalogue of known worlds includes entries that would have seemed implausible before they were found. Reality is stranger than fiction. Some of the most scientifically valuable recent discoveries orbit stars close to our solar system, worlds near enough that future instruments might characterize them in unprecedented detail. These nearby planets are prioritized for follow-up observation, precisely because their proximity makes measurements easier and more precise, allowing comprehensive study that more distant worlds cannot support. The solar neighborhood, defined as stars within about 50 light-years of the Sun, contains several thousand stellar systems, many of which have now been surveyed for planets using various detection methods. This nearby volume is not representative of the galaxy as a whole, being enriched in red dwarf stars and depleted in massive blue giants, but it represents the population most accessible to current and near-future technology. A discovery announced in 2024 added a planet to a star only about 12 light-years from the Sun, close enough that the host star is visible to the naked eye on dark nights. The planet is several times Earth's mass, orbiting at a distance that places it in the star's habitable zone, despite the star being significantly cooler than the Sun. The proximity and potentially favorable conditions have made this world a high priority for additional observations. Another nearby discovery from this period involves a planet around one of the closest red dwarf stars. A world detected through precise radial velocity measurements, accumulated over years of observation. The planet is too small to transit its star as seen from Earth, so its size remains unknown, but its mass suggests it might be rocky if its density resembles Earth's. The nearness of the host star makes it a potential target for direct imaging with future telescopes. The Proxima Centauri system, around the very nearest star to the Sun, continued yielding discoveries during this period, with additional candidate planets adding to the previously known Proxima b and c. The system has proven more complex than early observations suggested, with possible additional companions at various distances from the star. Sorting out the true planetary population around our nearest stellar neighbor remains an ongoing project. Nearby planet discoveries provide opportunities for atmospheric characterization that distant planets cannot offer, because brighter host stars produce stronger signals when starlight filters through planetary atmospheres during transits. Several nearby transiting planets have become high-priority targets for Webb observations, with atmospheric studies already underway or scheduled for upcoming observation cycles. The TESS mission was specifically designed to find planets around nearby stars, complementing Kepler's survey of more distant populations, with a catalogue of worlds close enough for comprehensive follow-up. This design choice has paid off in discoveries that have quickly become among the best characterized exoplanets known. with masses, radii, and atmospheric properties measured to precision impossible for more distant worlds. Radial velocity surveys have been particularly productive for nearby stars, accumulating observations over decades that reveal planets even when they do not transit. The longest-running surveys have now monitored nearby stars for more than 20 years, sensitivity accumulating to the point where Earth-mass planets might be detectable around the very nearest stars. Several recent discoveries have emerged from these long baseline programs. The nearest Sun-like stars have been intensively monitored, with researchers hoping to find planets in configurations resembling our solar system. These searches have revealed numerous planets, though none yet that closely mimics Earth in size and orbital location. The challenge of finding Earth twins around Sun-like stars persists, as the signals of small and observational noise can mimic or mask planetary signatures. The population of planets in the immediate solar neighborhood appears consistent with the broader galactic population, suggesting that our local environment is not unusual in its planetary abundance. Red dwarf stars nearby host planets at roughly the same rate as red dwarfs throughout the galaxy, and the distribution of sizes and orbital periods matches expectations from more distant surveys. The nearby planets are a representative sample of what exists everywhere. Future missions will specifically target nearby stars for planet characterization, including the proposed Habitable Worlds Observatory that would directly image planets around the nearest Sun-like stars. Such observations would reveal planets as points of light, rather than merely as effects on their stars, potentially allowing surface features or atmospheric structures to be detected. The nearby planets are stepping stones toward truly detailed knowledge of other worlds. The catalogue of planets within 20 light-years of the Sun now includes dozens of confirmed worlds, with many additional candidates awaiting verification. This volume of space, which seems vast by human standards, but is actually a tiny fraction of the Milky Way galaxy, contains more known planets than would fit in most mental lists. The neighborhood is rich with worlds. Some nearby planetary systems host multiple worlds, with several planets orbiting the same star in configurations that reveal gravitational interactions and formation histories. These multi-planet systems around nearby stars provide the most detailed laboratories for studying how planets form and evolve, with measurements precise enough to constrain models in ways that distant systems cannot. The investment in studying nearby planets pays compound returns, as each well-characterized world provides context for interpreting more poorly known planets at greater distances. The nearby systems establish ground truth that can be applied to distant populations observed with lower precision. Understanding a few nearby worlds deeply helps understand many distant worlds broadly. The coming years will add more planets to the nearby census as ongoing surveys continue and as analysis of existing data reveals previously unrecognized signals. Some of the nearest stars have been observed for decades without revealing planets. That improved analysis techniques applied to archival data sometimes extract signals that earlier methods missed. The nearby planet population is still being discovered. The stars visible in your night sky, the ones bright enough to see without telescopes, include many that now have known planets. Looking toward these stars means looking toward planetary systems, worlds orbiting suns that appear as familiar points of light. The sky has become more interesting as knowledge has accumulated, each star potentially hosting worlds that future generations might explore. The patience required to find planets around nearby stars through radial velocity methods spans years and decades, observing again and again to build up the signal that reveals orbital motion. This patience has been rewarded with discoveries that repay the investment many times over. The nearby worlds were worth waiting for. Several stars revealed themselves to host multiple planets during 2025, either through discovery of entirely new systems or through identification of additional worlds in previously known planetary families. These multi-planet systems provide unique scientific value, as the gravitational interactions between worlds reveal information that single-planet systems cannot offer. When multiple planets orbit the same star, they tug gravitationally on each other as they pass, slightly altering each other's orbits in ways that sensitive observations can detect. These perturbations reveal planetary masses without requiring radial velocity measurements, providing complete characterizations from transit data alone. The technique has proven particularly valuable for compact systems where planets pass close together frequently. One multi-planet system discovered during this period contains at least 6 worlds, making it among the most populous known. The planets span a range of sizes from super-Earth to sub-Neptune, packed into orbits that would all fit inside Mercury's distance from the Sun. The gravitational interactions among the planets are measurable and have allowed mass determinations for all 6 worlds. The system challenges formation models that struggle to explain how so many planets formed in such close proximity. Another notable multi-planet discovery involves a system where the planets are locked in a chain of orbital resonances, with each planet's period forming a simple ratio with its neighbors. Such resonant chains suggest that the planets migrated inward together during the system's early history, becoming locked in their current configuration by gravitational interactions with the disk of gas and dust from which they formed. The resonance has preserved a fossil record of that ancient migration. The TRAPPIST-1 system remains the most famous multi-planet example, with its 7 Earth-sized worlds packed around a dim red star. Ongoing observations continue refining understanding of this system, with transit timing variations revealing how the planets' masses compare to each other and whether their densities suggest rocky compositions. The system provides a test case for understanding how multiple small planets form and evolve together. Comparative studies of planets within the same system reveal how worlds respond differently to similar environments, with inner and outer planets showing systematic differences that track their varying distances from the host star. Some multi-planet systems include both rocky worlds and gaseous ones, demonstrating that diverse compositions can arise from a single formation environment. The intra-system comparisons are as valuable as inter-system comparisons. The architectures of multi-planet systems vary widely, from compact configurations where all planets orbit closer than Mercury, to spread-out arrangements resembling our solar system's broader spacing. Understanding what determines architecture is a major goal of exoplanet science, as the answer would reveal much about how planets form and migrate. Each new multi-planet discovery adds data that tests architectural theories. Some multi-planet systems include planets in or near mutual orbital resonances, while others show no evidence of resonant structure. The difference likely reflects different formation and migration histories, with resonant systems having experienced gentle inward migration that allowed locking, while non-resonant systems formed in place or migrated more chaotically. The mixture of resonant and non-resonant systems provides constraints on migration processes. The stability of multi-planet systems over billions of years requires particular orbital configurations that avoid close approaches and resonance crossings that could destabilize the system. Numerical integrations of multi-planet systems, found by Kepler and TESS, demonstrate that most observed configurations are indeed stable, persisting for the lifetime of their host stars without planets colliding or being ejected. The observed population has been filtered by stability requirements. Multi-planet systems around binary stars present additional complexity, with planets orbiting not one gravitational center, but two. The few known circumbinary multi-planet systems demonstrate that multiple planets can form and survive, even in these challenging environments. The formation processes that create such systems remain poorly understood, requiring models that handle the gravitational complexity of stellar binaries alongside planetary interactions. The search for additional planets in known systems continues, as many stars with one or two known planets might host additional companions that have not yet been detected. Planets in long-period orbits require extended observation baselines to confirm, and planets too small to produce detectable signals with current instruments might exist in systems that appear to host only larger worlds. The multi-planet systems of the future are hiding in today's single-planet catalogues. Young multi-planet systems provide snapshots of planetary evolution, with planets at early stages of their development when they are still cooling from formation and their orbits are still settling. Several recently discovered young systems contain multiple planets, allowing comparison of how different-sized worlds in the same environment evolve differently. These systems are particularly valuable for connecting formation theories to mature system observations. The total number of multi-planet systems known now exceeds 500, depending on what counts as confirmed versus candidate planets. This population is large enough for statistical studies that identify trends and test predictions. The multi-planet systems represent a rich dataset that will be mined for insights for decades to come. The gravitational dynamics of multi-planet systems operate continuously. Whether anyone observes them, planets tugging on each other in choreographed motion that has persisted for billions of years. The forces are mutual and perpetual, a cosmic dance that proceeds without pause. The observations we make are snapshots of motion that began long before Earth existed and will continue long after human attention turns elsewhere. Space telescopes capture public attention, but ground-based observatories continue contributing significantly to exoplanet discovery and characterization during 22-4 and 22-5. Telescopes on mountaintops around the world find new planets, confirm space-based candidates, and provide measurements that orbital instruments cannot make. The ground and space work together in partnership. The radial velocity technique, which detects planets through the tiny wobbles they induce in their host stars, operates primarily from ground-based facilities, where large telescopes with precise spectrographs can monitor stars night after night and year after year. This method has been responsible for thousands of planet discoveries, including many announced during the period under discussion. The Wobble Hunters continue their patient work. The HARPS spectrograph in Chile and its northern counterpart HARPS North in the Canary Islands have contributed numerous discoveries during recent months, detecting planets through velocity measurements precise enough to sense the gravitational influence of worlds only a few times Earth's mass. These instruments represent the current state of the art in radial velocity precision, capable of detecting stellar motions of less than 1 meter per second. Such precision reveals planets that earlier generations of instruments could never have found. The espresso spectrograph at the Very Large Telescope in Chile has pushed precision even further, aiming to detect truly Earth-mass planets around nearby sun-like stars. Results from espresso observations continue appearing, with claimed detections that approach the limits of what physics allows. With current techniques, the instrument demonstrates that ground-based radial velocity can compete with space-based transit detection for certain categories of planets. Ground-based transit surveys also continue operating, monitoring millions of stars for the brightness dips that reveal planetary transits. While TESS surveys the brightest nearby stars from space, ground-based surveys can access different stellar populations and can achieve continuous coverage through networks of telescopes distributed around the world. The NGTS and MARTH surveys have announced discoveries during this period. Direct imaging of planets from ground-based telescopes has advanced remarkably in recent years, with adaptive optic systems correcting for atmospheric distortion in real time and coronagraphs blocking starlight to reveal faint planetary companions. The Very Large Telescope and Gemini telescopes have captured images of several planetary systems, photographing young, hot planets that glow with their own infrared light. These images provide a different kind of data than transit or radial velocity detections. The atmospheric characterization of transiting planets can also be accomplished from ground-based telescopes, using high-resolution spectroscopy that resolves individual molecular absorption lines. This technique has detected various molecules in exoplanet atmospheres, complementing lower-resolution observations from space with detailed velocity information that traces atmospheric dynamics. Ground and space provide different views of the same atmospheres. The confirmation of space-based transit candidates often relies on ground-based observations that rule out false positive scenarios, like eclipsing binary stars or instrumental artifacts. A candidate identified by TESS becomes a confirmed planet only after ground-based telescopes verify that the signal is real and planetary. This confirmation role ensures that the exoplanet catalog maintains reliability despite the flood of candidates from space missions. The global distribution of ground-based observatories allows continuous monitoring that no single site could provide. With telescopes in Chile, Hawaii, the Canary Islands, South Africa, and Australia, collectively spanning all longitudes. When night falls on one facility, others are observing, maintaining coverage that approaches what space telescopes achieve. Networks like the Los Cumbres Observatory explicitly exploit this geographic distribution. The extremely large telescopes currently under construction will transform ground-based capabilities when they become operational later this decade. The European Extremely Large Telescope, with its 39-meter primary mirror, will gather more light than any telescope ever built when it begins operations in the coming years. This enormous collecting area will enable direct imaging of smaller, cooler planets than current facilities can photograph, potentially including rocky worlds in habitable zones around nearby stars. The atmospheric characterization capabilities will exceed what the James Webb Space Telescope can achieve for certain types of observations. Ground-based astronomy is entering a new era. The Giant Magellan Telescope in Chile will use 7 large mirrors working together to achieve resolution and collecting area far beyond current ground-based capabilities. The 30-meter telescope, planned for Hawaii or an alternative site, will add comparable capabilities in the Northern Hemisphere when construction challenges are resolved. Together, these extremely large telescopes will revolutionize our ability to study planets around other stars from Earth's surface. The collaboration between ground and space facilities exemplifies how modern astronomy operates as an integrated enterprise rather than a collection of independent observatories working in isolation. A planet discovered by TESS is confirmed by radial velocity observations from Chile, characterized atmospherically by Webb, and eventually might be directly imaged by extremely large telescopes. Each facility contributes what it does best, and the combined picture exceeds what any single instrument could provide alone. The scheduling of ground-based observations often responds to space-based discoveries, with telescope time allocated to follow up on promising candidates within days or weeks of their identification. This rapid response enables timely confirmation and characterization before public interest moves on to newer discoveries. The coordination requires communication networks that span continents and time zones, connecting observers and facilities around the world. The data from ground-based observations flows into the same archives and catalogs that store space-based results, creating unified databases that researchers can mine without needing to know where particular observations originated. The NASA Exoplanet Archive integrates discoveries from all sources, presenting a coherent picture of what humanity has learned about planets throughout the galaxy. The ground and space contributions blend seamlessly. The weather dependence of ground-based observations creates constraints that space telescopes avoid, with clouds and humidity sometimes preventing observations during critical windows. This limitation is balanced by the ability to upgrade and maintain ground-based instruments, extending their useful lives indefinitely and incorporating new technologies as they become available. Space telescopes carry fixed hardware, while ground-based facilities evolve continuously. The human presence at ground-based observatories connects exoplanet discovery to tangible places where people work through the night, watching screens and adjusting instruments. The high-altitude observatories in Chile, Hawaii, and the Canary Islands employ astronomers and technicians who experience the discovery process directly rather than through downloaded data files. This human element adds dimension to the scientific enterprise. The training of new astronomers often includes experience at ground-based observatories, where the connection between telescope and sky feels more immediate than when analyzing data from distant spacecraft. The nights spent monitoring observations, troubleshooting equipment problems, and responding to changing conditions create skills and intuitions that purely computational training cannot provide. The mountaintops remain schools as well as observatories. The economic impact of ground-based observatories extends to the surrounding communities, with employment, infrastructure, and scientific tourism contributing to local economies. The facilities in northern Chile have transformed previously remote regions, bringing roads and services that benefit residents beyond the astronomical community. The observatories become part of the landscapes they occupy. The future of ground-based exoplanet science includes instruments not yet built and techniques not yet developed, building on current capabilities toward goals that seem ambitious today but may become routine. The extremely large telescopes represent the next step, but steps beyond them are already being contemplated by researchers pushing the boundaries of what atmospheric turbulence and instrumental precision will allow. The partnership between ground and space will continue evolving as new facilities join the network, and older ones are upgraded or retired. The James Webb Space Telescope will eventually be succeeded by other space observatories, just as Kepler gave way to TESS. Ground-based extremely large telescopes will come online and eventually be superseded by still larger facilities. The search for planets and the characterization of their properties will continue through all these transitions. The discoveries of 2024 and 2025 include contributions from both domains, with space telescopes providing the systematic surveys that identify candidates and ground-based facilities providing the precision measurements that transform candidates into confirmed planets with measured properties. Neither domain works in isolation, and neither could accomplish what the partnership achieves together. The allocation of credit for discoveries sometimes becomes complicated when multiple facilities contribute to a single result. With the initial detection coming from one telescope, and the confirmation from another, and the characterization from a third, the scientific papers that announce new planets typically include authors from many institutions and acknowledge observations from facilities spanning the globe. Discovery has become a collective enterprise. The ground-based contributions to recent exoplanet science deserve recognition alongside the more publicized achievements of space missions, as the mountaintop observers work through nights that most people never see, accumulating the data that eventually appears in news announcements and scientific papers. The quiet persistence of ground-based astronomy underlies much of what makes headlines. The watchers on the mountains continue their ancient vigil with modern instruments. The specific discoveries attributed to ground-based facilities during 2024 and 2025 include several planets around nearby red dwarf stars detected through radial velocity campaigns. These worlds orbit stars too small and cool for TESS to observe efficiently, but well suited to the precision spectrographs of HARPS and ESPRESSO. The mass measurements these instruments provide reveal whether planets are rocky or gaseous. Several directly imaged planets were announced during this period as well. Young giant planets glowing with heat from their formation still dissipating billions of years after the systems formed. These images capture light actually emitted or reflected by the planets themselves, the most direct form of detection available. The images from VLT and Gemini show worlds that once seemed impossible to photograph. The transit timing variations detected by ground-based facilities have revealed additional planets in systems where one transiting world was already known, with gravitational perturbations indicating unseen companions. These discoveries demonstrate that multi-planet systems are common, and that patient observation reveals complexity that initial detections might miss. The systems grow more interesting with continued study. The ground-based contributions form an essential complement to space-based discoveries, and the exoplanet science of 2024 and 2025 would be significantly poorer without them. The telescopes on mountains continue earning their keep, night after night, year after year. The partnership between ground and space defines modern planetary astronomy. The accumulating discoveries of recent years, including those announced in 2024 and 2025, reveal patterns and raise questions that shape the direction of exoplanet research going forward. Individual planets matter, but the ensemble of discoveries teaches lessons that no single world could convey alone. The forest emerges from the trees. The abundance of small planets has been confirmed repeatedly by recent discoveries, with worlds between Earth and Neptune size proving far more common than the gas giants that dominated early exoplanet catalogues. This pattern, first suggested by Kepler's statistics, continues appearing in test discoveries and ground-based detections. The galaxy contains more small worlds than large ones by a substantial margin. The prevalence of these intermediate-sized planets, often called super-Earths or sub-Neptunes depending on their properties, poses challenges for theoretical understanding because no equivalent exists in our solar system. We have rocky worlds like Earth and Mars, and we have ice giants like Uranus and Neptune, but nothing in between. Understanding what these common planets actually are remains one of the major open questions in the field. Recent atmospheric observations have begun distinguishing between rocky super-Earths and gaseous sub-Neptunes, revealing that the boundary between these categories depends on mass, temperature, and stellar environment in ways that are still being worked out. Some planets that seemed potentially rocky, based on mass and radius alone, have shown thick hydrogen atmospheres that preclude Earth-like surfaces. Others appear genuinely rocky, despite sizes larger than Earth. The atmospheric stripping that red dwarf stars can inflict on their planets has been confirmed through observations of the TRAPPIST-1 system and other nearby examples, with inner planets showing little or no atmosphere, while outer planets retain their gaseous envelopes. This pattern has implications for habitability around the most common stars in the galaxy, suggesting that only planets at greater distances might maintain atmospheres suitable for life. The habitable zone might be narrower than hoped. The diversity of planetary system architectures revealed by recent discoveries continues exceeding what our solar system's orderly structure might have suggested. Some systems pack multiple planets inside the orbit of Mercury, while others spread their worlds across vast distances. Some planets orbit in near-circular paths, while others follow highly elliptical trajectories that bring them alternately close to and far from their stars. The possibilities seem endless. The correlation between stellar metallicity and planet occurrence, with metal-rich stars hosting more giant planets than metal-poor stars, continues appearing in recent data. This pattern makes physical sense because metals in the protoplanetary disk provide the solid material from which planetary cores form. Stars that formed from metal-enriched gas clouds produce more planetary building blocks. The occurrence rate of potentially habitable planets has been refined through recent discoveries, with current estimates suggesting that roughly 1 in 5 Sun-like stars hosts a rocky planet in its habitable zone. This fraction varies depending on exactly how habitable zones and rocky planets are defined, but the basic conclusion is that such worlds are common throughout the galaxy. Billions of potentially habitable planets likely exist in the Milky Way alone. The challenge of determining actual habitability from remote observations has become more apparent as atmospheric characterization has advanced. A planet in the habitable zone might be rendered uninhabitable by atmospheric composition, volcanic activity, lack of magnetic field protection, or countless other factors that transit spectroscopy cannot currently assess. The distance between potentially habitable and actually habitable remains large. The false positive rate for biosignature detection has received renewed attention following the excitement over K218b and the tentative detection of dimethyl sulfide in its atmosphere. Scientists have explored various ways that non-biological processes might produce molecules that initially seem to require life. The caution is warranted given the extraordinary implications of any claimed biosignature detection. The refinement of stellar properties through recent observations has improved planetary characterizations. Because a planet's size and temperature depend on accurate knowledge of its host star, better stellar radii from Gaia astrometry and spectroscopic analysis have led to revised planetary radii for many known worlds. Some planets grew larger in the updated catalogues while others shrank, as improved stellar data rippled through to planetary parameters. The masses of transiting planets have been determined with increasing precision through radial velocity follow-up, with recent discoveries including many worlds with mass uncertainties of only a few percent. This precision enables meaningful constraints on planetary compositions, distinguishing water worlds from rocky planets from gas-dominated worlds. The characterization depth has improved alongside the discovery rate. The eccentricity distribution of exoplanet orbits has come into sharper focus through long-term radial velocity monitoring that tracks planets through multiple orbits. Many planets follow nearly circular paths, like those in our solar system, but a significant fraction have elongated orbits that bring them periodically closer to their stars. The eccentric planets experience dramatic seasonal variations in stellar heating. The spin-orbit alignments of hot Jupiters have been measured through observations of the Rossiter-McLaughlin effect during transits, revealing that some planets orbit in the same direction as their stars rotate, while others are misaligned or even retrograde. These misalignments suggest dynamical histories involving gravitational scattering or disk warping that theories continue working to explain. The age dependence of planetary properties has become measurable through observations of planets in clusters and moving groups with known ages. Young planets appear larger than their older counterparts as they slowly contract and cool over billions of years. This evolution must be accounted for when interpreting the properties of planets whose ages are uncertain. The relationship between planets and debris disks has been clarified through observations that detect both planets and leftover planetesimals around the same stars. The gravitational influence of planets shapes the distribution of debris, creating gaps and asymmetries that reveal planetary presence even when the planets themselves cannot be directly observed. The disks become signposts pointing toward hidden worlds. The population of free-floating planets, worlds drifting through the galaxy without host stars, has received renewed attention through micro-lensing surveys that can detect these isolated objects. Recent estimates suggest that such rogues might be as common as stars, implying that planetary formation ejects enormous numbers of worlds into interstellar space. The spaces between stars may be surprisingly crowded. The period ratio distributions of multi-planet systems show evidence of resonant configurations where orbital periods stand in simple numerical ratios, suggesting that planetary migration shaped the final architectures. Other systems show no signs of resonance, implying different evolutionary histories. The diversity of outcomes from similar starting conditions remains striking. The atmospheric escape from close-in planets has been measured through observations of extended exospheres, with some hot Jupiters and sub-Neptunes visibly losing mass to space as stellar radiation heats their outer atmospheres. This ongoing erosion may transform planetary populations over billions of years, turning sub-Neptunes into super-Earths and eventually stripping some planets entirely. The theoretical implications of recent discoveries continue reshaping understanding of how planets form, migrate, and evolve over the lifetimes of their host stars. The models that seemed adequate a decade ago have been challenged by discoveries that do not fit their predictions. New models incorporate additional physics and explore wider parameter spaces to encompass the observed diversity. The formation of planets now appears to proceed more rapidly than earlier theories suggested, with giant planets potentially forming within a few million years of the protoplanetary disk's appearance. This rapid formation helps explain how giant planets can exist at all, since the gas disks from which they form dissipate on similar timescales. The race between planet growth and disk dispersal shapes planetary populations. The migration of planets through their natal disks has become a standard element of formation theories, explaining how hot Jupiters reach their close-in orbits and how compact multi-planet systems achieved their current configurations. The direction and extent of migration depend on disk properties that varied from system to system, producing the diversity we observe. The long-term stability of planetary systems has been tested through dynamical simulations that evolve systems forward for billions of years, revealing which configurations can persist and which eventually become unstable. The systems we observe have passed this stability test, but others presumably formed and were destroyed, leaving no evidence of their brief existence. The lessons from recent discoveries will continue accumulating as observations proceed, and analyses deepen, with each new finding adding to the body of knowledge that shapes understanding. The picture of planetary abundance and diversity becomes clearer with each passing year, though surprises continue appearing alongside confirmations of expected patterns. Learning never stops. The 2024 and 2025 discoveries fit into this larger context, individual data points that collectively tell a story about planets throughout the galaxy. Each world discovered joins a growing catalogue that statisticians can analyze for patterns, and theorists can compare against models. The individual and the statistical perspectives both matter. The implications extend beyond astronomy to questions about life's prospects in the universe and humanity's place in the cosmic context. The knowledge that billions of potentially habitable planets exist changes how thoughtful people consider these ancient questions, even if the questions themselves remain unanswered. The discoveries have philosophical weight. The story told by recent data is one of abundance and diversity, of planets everywhere and planetary systems of remarkable variety. The cosmos contains more worlds than any exploration could exhaust, more destinations than any imagination could populate. The discoveries continue revealing this truth with each passing year. The rate at which new planets are discovered has accelerated dramatically since the first exoplanet detections in the 1990s. And recent years have seen this acceleration continue as instruments improve and surveys expand their coverage. What was once a trickle of discoveries has become a flood that shows no signs of slowing. The pace itself has become part of the story. In the early days of exoplanet discovery, a single new planet could make international headlines and merit extensive discussion at scientific conferences. Astronomers knew the names of every confirmed exoplanet because there were few enough to remember. The catalogue grew slowly, with perhaps a dozen new worlds added each year, if the year was productive. The Kepler mission changed everything, revealing that planets could be discovered by the hundreds and eventually by the thousands when the right instrument observed the right patch of sky with the right precision. The catalogue expanded so rapidly that keeping track of individual planets became impractical for all but specialists. The flood had begun. TESS has continued the acceleration, discovering new planets at a rate that makes comprehensive tracking challenging even for dedicated researchers. The mission announces confirmed planets in batches, with dozens or hundreds validated simultaneously as analysis catches up with the accumulating data. The production line operates continuously. The current discovery rate approaches several hundred confirmed exoplanets per year, with additional thousands of candidates awaiting the follow-up observations that will transform them into confirmed worlds. The catalogues grow weekly, with announcements appearing so frequently that only the most unusual discoveries attract sustained attention. Abundance has bred familiarity. The comparison between current rates and those of just a decade ago illustrates how rapidly the field has evolved. In 2014, approximately 1,000 exoplanets had been confirmed. By 2005, the total exceeds 5,600. The catalogue has more than quintupled in just over a decade, and the growth continues accelerating. The James Webb Space Telescope has added a new dimension to this growth, not through discovering new planets, but through characterizing the atmospheres of planets already known in unprecedented detail. Each atmospheric detection represents a deepening of understanding that parallels the broadening achieved through raw discovery. The knowledge grows in depth as well as breadth. The infrastructure supporting this discovery rate has grown correspondingly, with data processing pipelines, analysis software, and archive systems scaled to handle the flood of information. The computer resources devoted to exoplanet science would have seemed extravagant a generation ago, but are now essential for keeping pace with the data. Technology enables discovery. The human resources have expanded as well, with more researchers working on exoplanet science than ever before, and more graduate students pursuing dissertations on topics that did not exist when their advisors were students themselves. The field has become a major enterprise within astronomy, attracting talent and funding that reflect its scientific importance. The publication rate for exoplanet papers has increased correspondingly, with hundreds of scientific articles appearing each year on topics ranging from individual planet discoveries to statistical analyses to theoretical models. The literature has become impossible for any single person to fully follow, requiring specialization and collaboration to navigate effectively. The conference presentations on exoplanets have grown so numerous that parallel sessions are required, with discoveries presented simultaneously in different rooms because a single room could not accommodate all the contributions. The annual meetings of astronomical societies devote entire days to exoplanet science that barely existed a generation ago. The near-term future promises continued acceleration as new facilities come online and existing ones extend their operations. The Plato mission, scheduled for launch later this decade, will search for transiting planets with capabilities designed to find Earth-sized worlds in Earth-like orbits around Sun-like stars. The mission will add to the catalogue while filling gaps that TESS and Kepler left unaddressed. The Nancy Grace Roman Space Telescope will contribute through gravitational microlensing surveys that detect planets through their gravitational influence on background stars. This technique is sensitive to planets that transit surveys miss, including worlds in wide orbits and free-floating planets that orbit no star at all. The census will become more complete. Ground-based, extremely large telescopes will enable direct imaging of planets that current facilities cannot detect, potentially including rocky worlds around the nearest stars. The ability to photograph planets rather than merely inferring their presence will transform how we think about them, making them more tangibly real. The Atmospheric Remote Sensing Infrared Exoplanet Large Survey, or RAIL, will characterize the atmospheres of hundreds of exoplanets, building a statistical understanding of atmospheric diversity that individual observations cannot provide. The mission will reveal patterns in atmospheric composition that inform theories of planetary formation and evolution. The longer-term future includes missions still in the conceptual stages, facilities that might not operate until the 2040s or beyond, but that are already being planned by researchers thinking decades ahead. The Habitable Worlds Observatory concept would search for biosignatures on Earth-like planets, a capability that no current or approved mission possesses. The growth in discovery rate cannot continue forever, as eventually the bright, nearby, easily detected planets will be found, and the remaining discoveries will require greater effort for smaller returns. But that saturation point remains distant, with current surveys still finding planets more rapidly than follow-up resources can characterize them. The backlog grows. The relationship between discovery rate and characterization rate creates a bottleneck, with more planets known than can be studied in detail, given available telescope time. The allocation of follow-up resources becomes a critical decision, with scientists competing for the opportunity to observe the most interesting targets. Not every discovery can receive the attention it deserves. The prioritization schemes that guide this allocation must balance multiple scientific goals, from understanding atmospheric diversity, to searching for biosignatures, to testing formation theories. Different criteria favor different targets, and the compromises reached affect which planets become well characterized and which remain mere catalog entries. The democratization of exoplanet discovery has proceeded alongside the acceleration, with data made publicly available and analysis tools shared freely among researchers worldwide. Scientists at small institutions can contribute discoveries alongside those at major observatories, and citizen scientists can participate through programs designed to harness public interest and attention. The international nature of exoplanet science has become increasingly pronounced, with discoveries coming from teams spanning multiple continents and facilities operated by space agencies from multiple nations. The search for planets is a human enterprise, not the property of any single country or organization. The commercial interest in exoplanets has grown as well, with private foundations funding search programs and companies developing technologies with potential astronomical applications. The field has attracted attention and investment from beyond the traditional academic and governmental sources that historically supported astronomy. The public interest in exoplanets has remained high throughout the acceleration, with news coverage of significant discoveries reaching audiences far beyond the scientific community. The question of whether planets like Earth exist elsewhere continues resonating with general audiences who may never read a scientific paper but who care about humanity's place in the cosmos. The pace of discovery has implications for how scientists think about their work. and plan their careers, with timescales for confirming theories and testing predictions shrinking as data accumulates more rapidly. Ideas that might once have waited decades for observational tests can now be evaluated within years, as new discoveries provide the needed evidence. The rapidity of change creates challenges for education, as textbooks become outdated quickly, and curricula must be continuously updated to reflect current understanding. Students entering the field encounter a landscape quite different from what their instructors learned, and today's students will find the field transformed again by the time they become senior researchers. The historical perspective on exoplanet discovery reminds us how recently this field emerged, and how dramatically it has evolved in just 3 decades. Scientists who made the first discoveries are still active researchers, watching the field they pioneered expand beyond anything they could have imagined. The founders have lived to see their work bear extraordinary fruit. The momentum built through decades of discovery shows no signs of diminishing, with institutional support, public interest, and technological capability all aligned to continue the search. The pace will fluctuate as individual missions begin and end, but the overall trajectory points toward more discoveries at faster rates for the foreseeable future. The acceleration continues. The planets discovered in 2024 and 2025, remarkable as they are, represent only the smallest fraction of worlds that exist throughout our galaxy and beyond. For every planet found, billions remain hidden in the darkness between stars, orbiting suns too faint or too distant for current instruments to survey. The known catalogue is a tiny sample of a vast population. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars, and current evidence suggests that essentially every one hosts at least one planet on average. This means that our galaxy alone contains hundreds of billions of planets, a number so large that comprehending it requires abandoning normal intuitions about quantity. The cosmos is crowded with worlds. The 500-600 planets currently confirmed represent perhaps 100,000th of 1% of the galactic population, a sample so small that statistical generalizations require careful treatment. The planets we have found are biased towards those easiest to detect, not representative of what actually exists. The typical planet may look nothing like the average discovered planet. The planets around stars too faint for current surveys remain entirely unknown, their existence inferred from statistics, but their individual properties completely hidden. The red dwarf stars that comprise the majority of the stellar population are mostly too dim for tests to observe efficiently, meaning that the most common stars have yielded the smallest harvest of known planets.
The surveys have sampled the unusual rather than the typical.
The planets in wide orbits, taking decades or centuries to circle their stars, cannot be detected through transits observed over mission lifetimes, measured in years. The giants in our own solar system would be invisible to transit surveys from distant stars, their orbital periods too long for the necessary repeated transits to occur within observing windows. Jupiter itself would remain undiscovered by Kepler's methods. The planets around binary and multiple star systems present detection challenges that single star systems do not. Yet binary stars are common throughout the galaxy. Many worlds orbit in these complex gravitational environments, experiencing double sunsets and intricate seasonal patterns that single-star planets cannot know. These worlds are underrepresented in current catalogues. The free-floating planets that drift through interstellar space without any stellar companion remain largely uncounted, detectable only through gravitational microlensing events that occur unpredictably and cannot be repeated. The rogue planet population may rival or exceed the bound planet population, meaning that most worlds in the galaxy might not orbit any star at all. The small rocky planets that might most resemble Earth are also the hardest to detect, their transit signals shallow and their radial velocity signatures buried in stellar noise. The worlds most likely to host life are least likely to appear in discovery announcements, their detection requiring precision that approaches the limits of current technology. The most interesting planets remain the most elusive. The planets in the habitable zones of their stars, receiving the right amount of energy to support liquid water, occupy a narrow range of orbital distances that surveys have only partially explored. Many habitable zone planets have been found, but many more must exist around stars not yet surveyed or at orbital periods too long for current missions. The potentially habitable population remains largely unknown. The moons of giant planets in other systems cannot be detected with current techniques, though they may rival or exceed the planets themselves in astrobiological interest. In our own solar system, Europa and Enceladus are considered among the best places to search for life, yet their equivalents around other stars are completely invisible. The exomoon population remains entirely undiscovered. The planets around stars in the galactic halo, the spherical distribution of old stars surrounding the disk where the Sun resides, have received almost no attention because these stars are distant and faint. Yet, these ancient populations have had billions of additional years for life to evolve if conditions permitted. The oldest planets in the galaxy remain unknown. The future will reveal many of these hidden populations as instruments improve and surveys expand their reach. But some planets may remain forever beyond detection, given physical limits that constrain what information light can carry across interstellar distances. The complete census of planetary populations is not merely incomplete, but may be fundamentally unachievable. The characterization of known planets will also deepen as observing time accumulates and techniques improve, with atmospheric compositions determined for worlds that currently show only sizes and orbital periods. The transformation from mere detections to characterized worlds requires follow-up observations that the discovery rate has outpaced. Many known planets remain mysteries despite their confirmed existence. The search for biosignatures will intensify as the James Webb Space Telescope continues operating, and future missions with even greater capability come online. The question of whether any discovered planet shows signs of life remains unanswered, but is being actively pursued. The answer, if it comes, will emerge from precisely the kind of patient observation that has characterized exoplanet science from its beginning. The patience required for these searches extends beyond individual careers to span generations of researchers, each contributing what they can during their working lives before passing the enterprise to successors. The scientists planning missions for the 2040s know they may not live to see the results. The work transcends individual lifetimes. The discoveries of 2024 and 2025 take their place in this larger narrative, recent additions to a catalogue that has grown continuously for 3 decades and will continue growing for decades to come. Each new planet confirmed is both an achievement and a reminder of how much remains unknown. The catalogue expands, but so does awareness of its incompleteness. The emotional resonance of exoplanet discovery connects to ancient human questions about whether we are alone, whether other worlds like ours exist, whether life might have arisen elsewhere in the cosmos. The scientific answers, when they come, will address questions that philosophers and theologians have contemplated for millennia. The technical and the transcendent intertwine. The night sky that stretches above you, wherever you happen to be, contains the stars around which these discoveries have been made and will continue to be made. Each point of light represents a sun that almost certainly hosts worlds, many of them unknown, some of them perhaps resembling our own. The darkness between the stars is full of planets. The quietness of the night mirrors the quietness with which exoplanet discovery proceeds, telescope by telescope and observation by observation, building the catalogue through patient effort that generates headlines only occasionally. The work continues whether anyone is paying attention, whether news coverage appears, whether public interest waxes or wanes. The search persists. The discoveries announced while you have been listening represent the current frontier, the newest worlds known to humanity, places that had no names and no confirmed existence until recently. These worlds orbit their stars in the same rhythms they have followed for billions of years, indifferent to being noticed, unchanged by their discovery. The finding matters to us, not to them. The researchers who made these discoveries worked through nights and weekends, analyzed data that seemed endless, and felt the satisfaction of contributing something new to human knowledge. Their names appear on papers that most people will never read, but their work becomes part of the permanent scientific record. The discoveries outlast the discoverers. The instruments that detected these worlds will eventually fail or be superseded, just as Kepler gave way to TESS, and TESS will someday give way to successors not yet launched. The hardware is temporary, but the knowledge it generates persists in archives and databases, accessible to anyone who wishes to explore them. The missions end, but the data endures. The questions that drive the search remain the same despite all the discoveries. Are we alone? Are planets like Earth common? Could life exist elsewhere in the cosmos? The catalogue of known worlds addresses these questions without answering them definitively. The search continues because the questions continue. The rest that approaches, if it approaches, comes in a universe revealed to contain vastly more worlds than anyone knew when exoplanet discovery began 3 decades ago. The knowledge of this abundance has become part of human understanding, background awareness, that shapes how thoughtful people think about the cosmos. We know now what we could only speculate before. The newest worlds discovered in 2024 and 2025 represent the current edge of that knowledge. The most recent additions to a catalogue that grows continuously. Tomorrow or next week or next month, more worlds will be announced, each one adding to the total, each one slightly expanding what humanity knows. The process never stops. The telescopes that make these discoveries operate through the night, gathering light that began its journey years or decades ago, from stars scattered across the solar neighborhood and beyond. The photons that reveal planetary transits and stellar wobbles travel for years to reach instruments that measure them with extraordinary precision. The light carries information patiently. The worlds yet to find outnumber those already discovered by factors of millions or billions, hidden in the darkness that current instruments cannot penetrate. Orbiting stars that surveys have not yet reached. The catalogue grows, but the unknown grows faster, each discovery revealing how much more remains to be found. The search will continue while you rest, telescopes monitoring stars, through whatever hours remain of the night, computers processing data that might contain signals of undiscovered worlds, researchers analyzing observations that accumulated while they slept. The Enterprise operates continuously across time zones and generations. The newest worlds are always being found, each month bringing announcements that add to the catalogue, each year bringing discoveries that challenge expectations and confirm predictions and reveal surprises. The pace accelerates even as the effort deepens. More worlds, more detail, more understanding. Rest now with the knowledge that the search continues, that the newest worlds of 2024 and 2025 are already being joined by newer discoveries, that the catalogue grows while you sleep. The cosmos contains more planets than you could count in a lifetime, and the counting proceeds without pause. Good night from the drowsy astronaut. Sleep well, and we'll explore the cosmos together again soon.